Hi, in this video we'll talk about VAR modeling. That stands for Vector Autoregressive Modeling. I know that we've had a couple of videos right before this where we talked about the theory behind it or the formulation of the methodology, and we saw that it was a big formula, and the formula is big enough that we surely don't want to be making calculations by hand. And I assured in those videos that we would be looking at the TSWGE code that will make it easy for us to make VAR forecasts for various data sets, and that's what we're going to do here. I also mentioned back when I just first described the multivariate time series chapter to you that a lot of the applications are in finance and economics because you hear a lot about leading economic indicators, things like that. And that is true that there are a lot of applications there, but not all. The one we're going to do here is more in the science area, and it's going to be about melanoma cases versus sunspot activity. So let's go on over into the R code and take a look at this. So this will be example 10.3 out of chapter 10, which is again is the multivariate time series chapter. And remember that our previous video where we were looking at real data was about MLR, multiple linear regression with correlated errors, but we're going to do this one by VAR. And again, the topic is melanoma and sunspot activity. And the first thing you'll need to do in order to do VAR modeling is to install and load the VARs package, library VARs. I've already done that, so because of that, when I run this, you're not going to see anything. But if you haven't done that yet, when you do, you're going to have to make a selection about a geographical location and all that. I'm sure you've done that in other areas of the book. So you have to install library VARs. Here's the general formula that we will use for VAR, and it looks like this. VAR, capital VAR, select, and then you give the arguments of the data set, X, give the maximum lag. We'll talk about that soon, about how you would make such a choice. These are the defaults: type equals constant, seasonality equals null, exogenous equals null. We don't really bother with changing those, so don't worry about those. Here's the data. The data is actually small data set here. It's only 37 years worth. It started in 1935 and goes up through 1972. Melanoma is on the top line. Sunspots on the second line. And we will go ahead and highlight those. Then also we're going to have a counter here. T equals 1 to 37. That's the 37 years worth. And then we'll define year. So we actually have a year number that makes sense. 1935 plus T. That'll make it easier to plot, which we're about to do right now. Let's take a look at that. So we're going to plot year versus sunspot and see what that looks like. And it has a surprising to me anyway, a pseudo-sinusoidal behavior. So quite cyclic, and I'm not sure that I expected that. Let's look at melanoma versus year. That one has more of a linearly increasing type look to me. I do see some up and down behavior, but it's erratic and hard to know when it's going to occur. So I can tell you this much. By looking at those first two plots, I don't necessarily see that, oh yes, one helps me predict the other, because I can see that 2 or 3 or 4 time periods ago, or one even, that it helps me know the future of the other one. Now, I will go ahead and add right now that history had shown, scientific studies had shown that there seems to be a 2-year lag between these two variables, meaning that in a year where there's unusually high sunspot activity, that is an indicator of 2 years beyond that there being higher incidences of melanoma cases. Now, I can't see that from the plot with my eyes, but I could sure use this CCF function. If you'll recall, I introduced that in the first video of chapter 10. At the very end of that video, the cross correlation function you can look at the cross-correlation function between these two variables, and that can help you decide whether or not you think that there is a lag that stands out and that it's one you need to certainly include in your model. So let's run this and see if we happen to see a spike at 2. Well, if a quick glance makes you say, I don't see any spikes at all in there, and maybe you're right about that. Nothing does stand out. But lag 0, here's lag 0, which is a very tiny little dip there. If we go back to, I will admit, it is relatively higher than anything around it. So that does maybe support the hypothesis that there's something going on at -2. So let's keep that in mind as we move along. Maybe so. Maybe there's something to this. Okay, this next little piece of code is going to look strange. Mel.64 and Sun.64. What's that? Well, what we're doing here is we're taking that melanoma data set and using the first 29 years of it to be our training data set, and then we'll test our forecasts on the last 8 years against actual data. Where's the .64 come from? Well, 1935 was the beginning of this. If we add 1935 plus 29 years, we get to 1964. It would probably be more clear if that said 1964, but that's where that comes from. So let's go ahead and do that. We're sectioning off the data set, and that's Mel.64 and Sun.64. Now, let's do this. Let's, first of all, just do a simple, I'll call it simple, univariate analysis, a time series analysis using univariate methods that we learned in chapters 1 through 9 of our textbook. And we'll also get the forecast. We'll do it for melanoma first. So what would we do? Well, we would say, all right, I'm going to let AIC help me decide. We'll call it an ARP. Let's don't get ARMA involved. We'll just say we're going to let our P go from 0 to 10. We're going to make Q sit at 0. That'll be the first thing. And let's ask what that P is that was chosen. And when we do that, we see that it picked a 1. So it chose an AR1 to model that first plot that we looked at, which was melanoma cases. Okay, fine. Let's trust that and say, all right, I'm going to have you estimate then that one parameter. There's the estimate for it. And then we're going to use the forecast function for.arma.wge and take a look and see how things appear. Well, my eyes tell me that, that's a very suspicious looking pattern. I don't really think that's what's going to happen. But remember, we sectioned off a test data set. We have actual. So let's do that next to see how our forecast truly did. So we'll plot year versus melanoma, and then we'll add these forecasts on and see what that looks like. Well, here come those forecasts that I said look suspicious. And, well, lo and behold, here's actual that's doing something pretty much quite the opposite. So this isn't a very good univariate analysis. This did not work. Even though AIC told us that an AR1 would model that, it's not doing a great job. Well, what about Sunspot? If we look at Sunspot, we'll do the same type of thing. The Sunspot was the very pseudo-sinusoidal pattern. I think I said the opposite of that just a minute ago, but the Sunspot is the very pseudo-sinusoidal pattern. Let's run this and see what AIC chooses as an estimate of P. It picks P to be 10. All right, fine. Well, let's estimate then the parameters, those 10 parameters. It looks like this, gives us this factor table, Let's try the forecasts. Hopefully they'll be better than in the melanoma case. And my eyes tell me that, yeah, that's got a chance. That looks pretty good. It looks like it completely repeated the pattern right before it. But again, let's check that with what's really going on. So we'll superimpose the forecast on top of the actual. And when I do that, I'm disappointed because I didn't realize that what was going to happen in actuality was that this wave, this sine wave, doesn't have a very high peak. It's really a pretty low one, and my forecast didn't catch that, and they went well above. It's not a poor job, but I mean, it's better than the melanoma, but it's still not very good. I would have to conclude that univariate forecasting has not done a very good job for either melanoma or for sunspot. So let's go down a different path here, and let's at this point say, let's try multivariate time series. And in particular, let's try VAR modeling. Well, the VAR select command likes you to have this data set in 2 columns. So we're going to bind those. We'll do cbind mel.64, sun.64. And I'll show you what that's going to look like. So there is the data set. And then we're going to do var select. There's that syntax that I said at the very beginning of the video. Var select dataset X, lag max equals 5, type equals constant, season null, exogenous null. Like I said, we're going to leave as the default. And let's see what happens here. We run that, and notice what we have. The selection says AIC picks 5. Let me jump over to the 3rd column. SC, that stands for Schwartz criterion. That's another way to say BIC. That's another way to say Bayes information criterion. That's confusing, I realize. But the 1st column is AIC. 3rd column is SC for Schwartz criterion. That's BIC. So we've got a 5 versus a 4. Hey, because VAR models are complex notationally anyway, let's go with the smaller one, and we're going to choose 4. And that's what we've said here, that we're going to go with 4. All right, next thing then, we'll fit the model then. We've chosen our P to be 4, and we're going to say VAR in caps, fit lowercase equals var dataset X, P equals 4, type equals constant. That's going to fit 9 parameters. I'll show you why in just a second. If you'll recall back to the previous videos, when we were looking at the formulation of the VAR, you may remember why this should have 9 parameters. Let's run this. And when we do, what we see is estimated coefficients for mel.64, estimated coefficients for sun.64, and sure enough, what we see is 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoops, I got off. 1, 2, 3, 4, 5, 6, 7, 8, and then plus the constant. And that makes sense to us because here's why. Remember, we chose a lag of 4, so we have 1, 2, 3, 4 lags on one variable, 1, 2, 3, 4 lags on the other variable. There's our 8 plus the constant term of 9. Now that happens per variable, per dependent variable. Mel.64 was one of the variables we're looking at. The other one was sun.64. So there'll be 9 for one and 9 estimates for the other. Again, pretty heavy notationally, but if you wanted to spell out or list out the model, write out the model, you would need to know these coefficients. Okay, let's do something differently than write out the model, and let's look at forecasts. That's what we're interested in at the moment. So what you do is you use the predict function, and you say predict var fit in ahead equals 8.